So now in this video, we're going to look at the non-inverting comparator circuit again, but we're not going to use 5 volts. We're going to step up the voltage here. I have lithium iron phosphate batteries, as do a lot of other people. So we're all going to probably want to make a bunch of circuits using those batteries to power them. That's the pin layout for the LM358. The LM358 can easily handle lithium iron phosphate battery voltages because with a single supply you can put up to 32 volts and to power the circuit. And if it's a dual supply, that means there's a positive voltage and a negative voltage in relationship to ground. That's actually where you would put the negative voltage. Same with over there. And ground would be a halfway point. But any case, we don't have that there. We just have a single supply of the positive supply and ground, which is the negative supply in this case. So the main thing when it comes to using this voltage range with the op amp, as I said before, it can easily handle it. If we are using resistance-based voltage dividers, it doesn't really matter the voltage. Whatever we set the trim pot to, it's got to be above halfway or below halfway for what we set to the inverting input there. That's the non-inverting input. And so really this doesn't change. 10K, there's a couple 10K, so that's 20K total. Can easily handle 14.6 volts, which would be the voltage that a lithium iron phosphate battery charger might apply to the battery. So that's if the charger is applied and it's 14.6 volts. Once you remove the charger, it drops right down to 13.6 volts. So you may not even ever deal with that if you never power the circuits when a charger is applied. The main challenge is these resistors here that protect the LEDs, and also they can't overheat, and also you have to limit current through the output there. I think somebody that replied to one of my videos was having problems with getting the LEDs off, maybe because they were using too low of a value of resistors. The red LED is being protected, and this is when the output's high right there. Red LED is going to drop about 2 volts. So let's just use 15 volts to make the math easy. That means we might have a maximum of 13 volts across this resistor there. So the 1.5K resistor should limit current, but make the LED bright enough. And I'll try to put the math on the screen right there. I just looked to make sure the LEDs were bright enough. I didn't really do the math. And also, when you're dealing with 13, I think even 15 volts, 1.5K, 1,500 ohms, seems to be pretty good at not exceeding half of its maximum wattage rating. So most resistors are rated for 1/4 watt, and I think this resistance keeps it below 1/8 of a watt, maybe even if you put 15 volts directly across it. Now the red LED is going to drop about 2 volts, and then the output falls a bit short, especially with the positive supply there. And it gets worse at higher currents. But in any case, we are dropping some voltage, so that should be plenty of resistance to keep the resistor from overheating, and then thus allowing enough current to get the LED to light up. These outputs aren't really meant to power loads. They can provide enough to light LEDs though. So you don't want to be trying to crank a lot of current out of these. You would use this output to switch transistors to turn loads on and off or do other things. You don't want to really try to power loads directly, but you can LEDs because they don't need much current. Now, the blue LED, it's a lot brighter than the red LED at the same current. It does connect to ground to the op amp better than the positive supply. But in any case, we have 3K just to kind of cut the current about in half through the blue LED versus the red, because the blue is brighter at the same current. So if you cut the current in half for the blue one, it's probably going to be about the same brightness as the red LED. So that's the basics. We won't look at the schematic when we look at the circuit. The trim pot is connected to the non-inverting input, plus output wants to be more like the non-inverting input than the inverting input. And the inverting input will have half the supply voltage. So at 12 volts, it'll be about 6 volts. 14.6 volts, it'll be about 7.3 volts right there. But it doesn't matter. It's about half of the supply voltage. So the trim pot, if we're above halfway, then we will have a higher voltage than what we got there. We'll have a high output. If we drop it below about halfway, then it will have a lower voltage, the non-inverting input, than what the inverting input has. So it'll be lower, thus the output will be low. The blue LED will light up. And so now we got the power supply. It is off though. I'll turn it on. So there, you can see the blue LED is, you know, relatively bright. My lamp's at its brightest setting. If I dim it, the LED will look brighter. But that's just because the camera is adjusting the total light. So yeah, as long as I stay down in this lower region, the blue LED stays lit up. You can see we got positive supply above it. And now if I go up about halfway, now the red LED lights up. And you can see about how much current, that should be about, all of that should be about the LED. There shouldn't be much current there, but it might tick it up. You know, if like it's right on the edge of 6 and 7, that extra current might bump it up to 7. But it doesn't really have much current compared to what's going through the LEDs. So there you can see about 4 approximately. And there about 6, you know, approximately. So quite a bit less going through the blue LED than the red LED, but they are about the same brightness right there. It looks like the blue LED is a little bit brighter. You can adjust the resistor values if you want, but if we go up to 14 volts, 14.6, I think you really want that 1.5K right there. So the red LED will get brighter as we bump up the voltage. So yeah, there's an op amp there, but we're not using it. Same pin layout though as this one, other than it shuffled down. So output, inverting input, negative, and then the non-inverting input, the plus, right below that. So trim pot, fixed resistors of equal value, doesn't matter their exact value, and then the output there going to the load. And now we will change the supply voltage. So I hit set right there, move over to that digit, and I have current limited in case I screw this up. And we could go up to, yeah, let's just go up to 15 volts. So we should still be okay at 15 volts, but technically a lithium iron phosphate battery is going to end at about 14.6 volts if a charger is applied. Won't even be that high by itself. And there you can see we got, you know, somewhere close to half there through the blue LED versus the red LED. Not perfectly half, but in that range. So it worked perfectly fine. At 15 volts, the red LED is pretty bright, even 13.6 right there. It does look like it's still pretty bright. I do have the lamp at the highest setting. There you can see I dim it. So I think this is okay. Now, the nominal voltage of a 12 volt lithium iron phosphate battery is actually 12.8. So about if you go from fully charged to fully discharged, this is going to be the middle ground voltage. And also it has a pretty flat voltage. So even though it kind of looks like we have a wide range going up to 13.6, it rapidly drops to close to 12.8 and hovers at 12.8 for a long time before it kind of rapidly drops to 12 and then down to like 10 if you want to, you know, 100% discharge it. So the vast majority of the time, if you have a lithium iron phosphate battery, your voltage is going to be in the range of about 12.8. Hopefully that makes sense. So in any case, this video went on really long, so I hope you enjoyed. Make sure you check out one of the other videos I'm posting to the screen, and check out the links down below. They all help out a lot. I'll see you in the next video.